Okay, so today it's focus on this. Is that an inverse? No, it's the other thing. Starts with an R. What is it called? Reciprocal. All right. So we're doing reciprocals. So we've done a lot of things to functions. We've said, is this function even or odd? That was in this unit. Okay, we'll review that stuff all tomorrow. I'm going to just try to get right to what we're doing with this. We've added functions, f of x plus g of x. We have subtracted functions. We have multiplied functions. We have made functions eat other functions, f of g of x. Now we are doing 1 over the function. Hold on just a second here. And so to do this, I want to make an XY chart of a bunch of points, and I just want you to copy these down. 2, 4, 3, -4, 4, 8, 5, 10, and I would like you to just take a guess what that does. If this is the parent, pausing for a second. I'll bet you some of you were able to go, well, f of x actually means y. So I'm going to take all the y values and make them 1 over that. So instead of 4, -4, 8, and 10, I'm going to make it 1/4, 1 over -4, or -1/4. 8 divided, 1 over 8 and 1 over 10. All right. I'd like you to just process for a second. Do you get when I started to get big Y's that I now got really small numbers? If it was really big, putting 1 over that makes it really small. Okay? All right. So if you only had a 1 in the first place, and you put 1 over a 1, what would have happened? Still would have been 1. It wouldn't have even changed. So you can't say putting 1 over something makes it go and get really tiny. It depends on what it was in the first place. So let's add a couple more points to my chart. Please do this with me. Let's go 5, 100. We don't even have to actually graph this, but we're just going to think about what would happen if. And then what would happen if it, I shouldn't say 5. Make it 8, 100, because otherwise, what would have been wrong with saying 5, 100? Wouldn't have been a function anymore. Okay, good. Because it wouldn't have passed a vertical line test. But if I make it 9, 1/10, please figure out what these turn into. When you take 1 over something. Okay, so on that 100, do you get that's going to change to 1 over 100, almost 0. Would you agree 1/100th of something is extremely tiny? It's approaching, that's what we say in math, and so when we say it, it's not actually 0, but it's getting there, we say it approaches 0. That's something you're going to learn in calculus next year. Most of you will take calc next year, whether you take the IB version of it or the AP version of it, or you just take regular old high school calculus. Usually that's what kids take after this class. And then they talk a lot about limits and how things approach something. Like when you get really close but you never actually get there, that's called asymptotic behavior. It's getting really, really close but it never gets there. That's like this. All right. And then the 1/10, when you put 1 over that, that's the whole point, 1 over things. 1 over 1/10, I want you to process that for a second. Do you know that when you put 1 over something, it just flips it over? If you didn't know that, it's true. So if I had 2/3 and I go, wait, I want to do 1 over that, it just makes it into 3 over 2. If If you want to know why that is, would you agree that 1 is the same as 1 over 1? And then right off the top 20, you can take this, change it to multiply by, and flip it. And then guess what happens when you multiply something by 1 over 1? It's the same. So there you go. If you have a fraction and then you flip it, or sorry, then you do a reciprocal, then you just have to flip that fraction over. Okay, so if I had 1/10, I just flip it over and it's 10. What's the theme here? When you do the reciprocal, if something was really big, like 10, it turns really small. And when something was even really, really, really big, like 100, it gets really, really small. It approaches 0. It gets really close to 0. So the bigger the function is, when you do the inverse to it, or sorry, not the inverse, the reciprocal, the bigger the function is at that moment, the smaller it'll get. And if it was really small, then it gets bigger. Okay, so knowing that ahead of time, now I think we can go into the notes and have it be okay. So there is a function. Let's name a few points that it goes through. It goes through 0, 0. I think we don't need to label that one, but this one's 3, 5. I'm writing 3, 5. Because do you get, I can just do what we just did. And the new function, the reciprocal, will be 3, 1/5. It'll be about there. When the function was really high, now it's going to be really low. How about it's 0, 0? When you flip a 0, do you know what you get? Still 0. So, all right, wait a minute. No, you don't actually. When you flip a 0, you get 1 over 0. That's not 0. It's like, remember me saying that when you flip something that's really small, you get something really big? Would you agree that 0 is the ultimate really small thing? No. Yeah, it is. And 1 over 0 is the ultimate really big thing. It's like infinity. Okay, we'll process that more in a second. So let's do a few more normal points first. Let's take this kind of normalish spot here. Would you agree that that looks to be about 4.5-ish? I know it's not exactly. Comma 3. Well, then it's 4.5, comma 1/3. That's off. These little fractions are challenging to do. That's still off. Maybe there-ish. Okay, now let's take one that's even smaller, like here. And that's a really important one. That's going to be 5.5, comma 1. When you have a 1 here, it's the only number. No, actually, there's another. You'll figure it out in a second. That when you take 1 over it, it stays the same. What is 1 over 1? It's 1. So that stays the same. So that spot right there will stay exactly the same. This spot is different. This spot was different. All right, let's do another one. Let's say that this went through 1, comma 2. I know it's off a smidge, but let's just say it was close enough to round to 1, comma 2. Then what will it be now? 1, comma 1/2. Next, would you agree that this spot is about 1/2, comma 1? So what'll it turn into? It'll stay in the exact same spot because its y value is 1. So these points are kind of precious. This one and this one. And I can all of a sudden just go right over here and say that one too. See what I did there? I knew that at that moment the y value was 1, so when I flip it over it's still 1, so those are points that will stay the same. Now let's connect the dots. Do you see that where the other one was at its highest, the purple one, where the purple one's at its highest, our new function is at its lowest. And then it has to go through these other points. But then we still have to get that 0 thing straight. 0, when it hit here, I'll make it green. That spot, and this spot, and this spot. Do you agree the y is 0 in all of those spots? Then what the heck is 1 over 0 again? No solution, but it's not only that, it's an asymptote. Everybody draw an asymptote line through there, and there, and there. All right, now I can answer your question. Is that it? Okay, good. You're right. All right. Now, if my answer is the green asymptotes with the blue line, do you understand asymptotic behavior? Do you get that the function will be drawn closer and closer to that line but never touch that line? Whoop. Whoop. Why? Because as you get closer and closer to that line, let's investigate a point here. Let's say that this point right here is the one we care about, and we're going to convert that over to the new system. Well, it's at like 1/5, comma, oh, I don't know, some other small fraction. It's about maybe 1/3. That's where that point is now. And then it'll be at 1/5, comma 3. So it'll be like way up here. Now granted, I'm off a smidge on my line. Maybe I'll adjust that then. So maybe I need to go through that line. And you could keep doing that with points, or you can start understanding the big picture that when you get asymptotes in there, your lines will have to approach the asymptotes. Now, I sometimes get asked the question, is there an asymptote on the x-axis, going the other way? No. There's the Great Wall of China. You cannot go through that. Why? Why can you never have the function drop through the x-axis like this? Because at that moment, it's changing from negative to positive. By putting 1 over something, are you ever going to change something from negative to positive? By just putting 1 over it. Do you get what if I put 1 over something? I can't change if it's positive or negative. So you won't cross this line, but it's not an asymptote. So this axis right here, you won't cross it, but you also don't act like an asymptote and have to get really close to it. The original function crossed it. The original function can do whatever they want. But when you're making not an inverse, but a reciprocal graph, you won't be able to cross that. I like to think of it as a wall. And the asymptotes, you get closer and closer to. The x-axis, you don't. You just can't cross it. Yes? I want you to say what you were saying, but then you stop because you didn't like the answer. Because the numbers are getting smaller, then the other one's going to be getting bigger. Yeah. Yes. For the asymptotes. For the asymptotes, just draw a dotted line down through the...
No, because it crosses over and the graph's already written. When it crosses over, would you make a dot in the line?
Okay, so I'm agreeing that the green dotted line, the asymptote, crosses over our original function, the purple function. But we don't have to do anything to the original. At the end, the original is going to just disappear, and the only thing left in our graph is the blue stuff, the new function, and the green stuff. So no, I don't have to do anything. I don't have to make a hole there because that purple is just there to show us what the function used to be. And the function, before I started messing with it, it went through 0. And so it's not like there's a hole there. Okay, I hope I answered your question. But at the end, just know this. We don't care about the purple line anymore. It's just going to be erased. And the only thing that'll be left is our answer. All right, now, that was the really slow way to do this. I'm going to show you this next part of the graph the really fast way. Well, I know -1 is going to just be 1 over -1. So those are the spots that are going to stay the same. Wherever this got really low, my new graph is going to get really high. So I'm going to generally go like that. Do you see what I did there? I could take it point by point, and if I get lost, that's what I would do. I go, okay, I think this is the point -3, -2, so I'm going to make it -3, -1/2, and look at that, it's about right. See what I mean? But I just find these key spots there and there, the spots where it goes through 1, which is 1 over that, won't change. And then I know it gets lower when the other gets higher and vice versa. And then asymptotic behavior. Going to get really, really close to the asymptotes. Boom. See, I'm done. Once you get how these work, this isn't that hard. Okay, about the end piece here. I marked this wrong more than anything else. So be careful on these. And I get why people get confused. Okay, but if I know it's asymptotic behavior and this is the Great Wall of China down here, I cannot cross that, then do you get which way the asymptote has to go? I get that it goes this way, but you might not. I don't know. But then this would be the brutal part, is kids just leave it like that. And they have acted like there's no graph here. You get that wrong, because you have to have, you have to finish. And what's happening to the purple equation in this little zone here? It's getting what? Bigger and bigger, so what's the other one going to do? Get smaller and smaller. Is the x-axis an asymptote? No. What do I say it acts like? The wall. Yes, you can't cross the wall. It stood up for thousands of years, kept out the invading hordes. The Great Wall of China did its job. It won't let you cross that. Why can't you cross it mathematically? Because that would be making a y value go from positive to negative just because you put 1 over it. By making this, all we're doing to our function is putting 1 over its y value. So how could it change from positive to negative? By just putting 1 over it. All right. I'm going to double check it, and you know which parts I'm going to check to make sure I didn't screw this up? The ends. Usually people get the middle part right once they understand these. And then I'm going to check here and make sure as this got smaller and smaller here, smaller, 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 then the other graph got bigger, 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 and it did. And then over here, as the graph got bigger and bigger up in this area, then this one needed to get smaller and smaller. Yay, I think it's right. There, you did your first, what is this called again? Reciprocal. Very good. All right. Let's just draw 1 over x. Everybody, can you just graph 1 over x for me? If you're like, dang, which one is that? Then you don't know your functions well enough. You've got to get these down so they're like, oh yeah, that's easy. Just like if I said the parabola, you'd be like, well, it looks like that, of course. All right, 1 over x. The key spots are here and here, and then it goes like this and like that. There's my original function. And they want me to do the reciprocal of that? Yes. All right, so what are the key places? Those 2 dots. Because they're there where y is 1 and negative 1. I mean, it is 1 comma 1, and it's negative 1 comma negative 1. And remember, it's all about the y values here, because we're doing 1 over the y values. That's what the reciprocal is. Sorry. Yep, reciprocal. Okay. Oh, thought I said the other word. It's so easy to get them confused. All right, so what do I do? Well, I know this much. These two spots aren't going to change. Last time we had the guiding light of the asymptotes in the right spot. There aren't any asymptotes this time, because our original function never touches the x-axis. So then we got to just go by this. Would you agree in this zone, my numbers, my y values just get smaller and smaller and smaller? So what should our function do? Bigger, bigger, bigger. We could even get specific points if you wanted to. You know, if we say that that's like 1, 2, 3, 4, 5, then this would be 5 comma 1/5. If you ever get lost, just go make a few points. So then it would be 5 comma, flip the other number. 1 over 1/5 is 5, 5 comma 5. So I go over 5 and up, 1, 2, 3, 4, 5. There it is, see? Okay. The y-axis is like it's not even there. We don't care about it. It's not like the Great Wall of the y-axis, just the x-axis. Do we still have that rule about the x-axis? Yes, we do. Because we can't change a number from positive to negative. So we can't go across this. This is the Great Wall still. Okay. Well, what do I do now? Well, would you agree this is getting bigger and bigger? Then the other one needs to get smaller and smaller. And this is going to get infinitely big. When it does, when the blue one here got infinitely big, then the other one gets infinitely small. It gets incredibly close to 0. All right, let's do the same thing on the other side. When this gets a really big negative, like, you know, -5 or something, then this will get to be a small negative, or infinitely close to 0, but not crossing 0. Okay, and then as this one gets really small, then this one will get really big. And now if I just kind of clean up how it attaches to that center. If you get infinitely close to, go ahead.
One over x. So it's a straight line with a hole at the origin, I think.
Yeah, isn't it y equals x?
Okay, hold on. Hold on. Are you saying that the blue one is messed up?
No.
Are you saying that the red one is messed up where?
It just shouldn't it be straight?
It should be a 1.
I think it'd be like straight lines in there.
Because it should be 1
1,
over
2, 2, 3, 4, 5.
Because if it's 1 over f of x, then it would be 1 over x, which is x, yeah. And then there's a hole at 0, 0.
Yeah.
I agree with the hole at 0, 0, but you're saying this should be a straight line?
Yeah.
Yes.
Here. Zoom out to the f of x equals
All right,
1 over
so
x.
so let's do it by points, because I know that if I'm a little confused by what you're saying, then other people probably are too. Would you agree that on the blue line, we can name all the points because the function is known. So we know it's the 1 over x function. So if y equals 1 over x, then if I say x is like 1/5, then y would have to be 1 over 1/5, which would be 5. Like, so this has a point on it of 1/5 comma 5. So that's like up here. 1/5 comma 5. So then let's take that point and say, I'm going to find now the reciprocal of that one. And so it'd be 1/5 comma 1/5. I see what you're saying. 1/5 comma 1/5 would be like right here, and 1/4, 1/4, and then 1/2, 1/2, and yeah, I get what you're saying. Very good. But yeah, that whole hole at 0 thing, let's talk about that. It's gonna freak some of you out. How close to 0 are you getting? Infinitely close. Okay. If you're infinitely close coming in from both sides, if you're infinitely close to something, then how about the point 0, 0? Could we ever have the point 0, 0? Okay. But how close are we to it? Infinitely close from both sides. So when you graph this, expect your calculator to have a line going right through 0, 0. Why? If the calculator is going to get infinitely close to it, it can't say, oh, but I'm going to stop now and leave a hole that's big enough for you to see. So it's going to go right through it, but you can leave it empty like that. Because, yeah, how on earth is the answer supposed to come out to 0, 0 when you did 1 over something? How can 1 over something be 0? Okay, yes.
So then you would draw like an open dot.
Yep, an open dot, yep. That's called a hole in the graph, yes.
So there wouldn't be an asymptote, so for 1
No
over x,
asymptotes on this whole graph.
so for 1 over x, there isn't an asymptote for y, or there is?
For the original function, there was asymptotes, yes. But that doesn't mean there's asymptotes on the new function. Okay. All right, so I may not have been drawing that right in the past. So you guys got me on the whole, this is a straight line in here, and that kind of freaks me out. In this little box here, that would be a straight line. Cool. You showed me how, because if it was 1/5 5, then that would be 1/5 1/5. And if it was 1/3 3, then it would be 1/3 1/3. So, yeah. Yes.
I think there would be a straight
It's
line
just
for
y
the
equals
rest
x,
of them.
like 1/3 3, no, 3 1/3 would make it 3 3.
And then-
Are the rest of them straight too?
Yes, it's just.
No. I think your logic would apply though. So if I keep getting points and I go, if this right here is, oh, that's a gross point. 2.5, comma a half. 2 1/2, comma 1/2. Then wouldn't that,
No, it's
oh,
it's just a
because it
bad
wouldn't
drawing.
actually, yeah, you're right.
5 halves.
It would have to be
2/5. What half of this?
2.5.
Because 1 over x is.
5 over 2, you're right, 5 over 2, comma 2 over 5. And then you flip it over and it'd be 5 over 2, 5 over 2. You are right. Weird, it is straight. My brain hurts. Yup. I think I've always skipped over this problem in the past because it was so complicated. But I feel like a better person for having worked it through with you guys. So, nice job. Almost always we have curves in them. In our answers, in our results to these. Okay, at least do you know that this is what 1 over x squared looks like? You should memorize that one. Then, are there asymptotes on the original? Yes. Does that mean there's asymptotes on this other one? No. Would you draw what you think the reciprocal of this would be? And if you have to, you can go point by point. Name each point that's on the 1 over x squared graph and then make it flip. Yes?
I feel like for like this one and the last one, it's easier to do it like from the formula, like 1 over f of x equals 1 over x.
Okay, agreed. So, what do you think the answer looks like?
It's x, f of x equals x squared.
Parabola with a hole at the origin.
Like that? But it's curving now. How come it's curving?
Because it's
So, if this stays the same, right? And this becomes 1 over that. So it'd be 1 over x squared. And what does that mean? 1 over x squared, because we just took this and flipped it over because we're doing the whole reciprocal thing. So then that's just x squared. And look at that, it's x squared. But wait, that would go through 0, 0.
Does that mean
Can it touch 0?
Wait,
You sure?
yeah, because it's just x squared.
No, if it's 1 over
Because
x
it-
squared, 1 over 0 squared, it still doesn't work.
Because it's an asymptote in the original function, just like the last one.
Whole. But yeah, because if you take the answer and just say, well, the answer would have to be 0, 0. How would you have gotten 0, 0? 1 over something would have had to be 0. And what could you have? 1 over anything? Can you think of anything? 1 over anything could be 0? All right. We're getting into really weird ones. We need to get back to like more normal ones. So I'm going to give you one more normal one. Don't go to the next slide. It's not normal. Here's a normal one. Would you agree that is a nice, simple curve? Okay. Now I'm going to tell you where it's 1 because otherwise it'll be really hard. We're going to say it's 1 right there and there. And it's -1 right there and there. Why are those so important? Because those are the spots where when you go 1 over 1, it doesn't change. Can you graph, if this is f of x, can you graph with blue or some other color 1 over f of x? If you understood what I've been trying to teach you there, I know those last two got really complicated, but I think they're kind of cool, but it might have confused people. Just remember, when the original function gets bigger and bigger, the reciprocal is going to get smaller and smaller. When the original function gets really, really close to 0, the other one gets to be 1 over that, which is like the opposite of 0. It's like huge. All right, how many of you remembered that at 0, 0, or the spot where it hits 0, you had an asymptote there? Raise your hand if you had that right. Good, that's huge. Because then if you remember that this is the Great Wall of China, then we can just use our knowledge about asymptotic behavior. It has to go up that way, it has to go up that way, and then when this gets higher, this gets lower. There we go. Where did I say I'd marked most things wrong? On the ends. Let's be careful here. Asymptotic behavior, it can't go that way for asymptotic behavior and get closer and closer to that because that's not an asymptote. The asymptote's here. This one, it will get, yeah, because this one's going to get infinitely big. Then the other one will get infinitely small. It will act kind of like an asymptote. Oh, it's too many things in life that are like, you shan't ever say never or always. So it's basically saying never say never. Deep. Vivian, come on up and get this, please. And I love your giant list of things you're interested in. Me too.
I have to leave at 9:25.
All right, so I finished off the last little part here. As this got smaller and smaller, this got bigger and bigger. That's also getting closer and closer to the asymptote, which made sense. I made this have a hard stop to it, then I'd have to hard stop my function. Don't worry about the little curve difference there at the end, no big deal. Okay. That's a normal one. Let's go to one that's tough. Would we ever give you a tough one? Well, I don't know. That's called honors pre-calc. Maybe we would. Now, at least on this one, you know where ones and zeros are. You can see where it hits 0, and you can see where it hits 1, and those are the key spots. And then you just got to know the whole, when it gets bigger, the reciprocal gets smaller. I'll pause for a second while you try this. Okay, some starting places. Hopefully you knew that these spots were important. They are all places where it hit 1, and the answer will go through those because 1 over the y value will still be 1. And all the spots that it's -1 are also equally important because 1 over -1, it'll go through those too. Next, asymptotes. Whenever the red function hits 0, we would have to do 1 over 0, which can't exist. So asymptotes there and there, and there, and there. Missed it, but I was close. And there, and there. Okay. Clean up my asymptotes a little bit. That one could do better. Okay, and now when this one gets bigger, this one gets smaller. Oh wait, I'm underneath the 0. Oh, that can't work. Okay, I'm gonna try that again. It has to go closer and closer to the asymptote. Closer and closer to the asymptote. Enjoy your day.
Thank you, you too.
Closer and closer to the asymptote. Closer and closer to the asymptote. But as this one gets like a bigger and bigger negative, then this will be a smaller and smaller negative. It's weird, but there will be a gap there. All right, now asymptotic behavior. Ba-doop, ba-doop. Oh, this one has to obey the asymptote laws. Closer and closer to the asymptote. And then when this was getting bigger and bigger, the other one should be getting smaller, smaller. If you ever get lost in something like that, then just take a point like this and say, where is that? That's -4, 3. So it needs to be at -4, 1/3. Like down here-ish. And then, where did I say I would mark it wrong the most? And the ends. Do you see how I never even did the ends? People forget them, or if they do them, they're not careful. Like here, there was a hard stop on it. So it stops right there. It does not go past that. And same with this one. It was not an arrow, so it's a hard stop at 1, but asymptote going that way. There we go. Whew, tricky business. But that's the last new thing. And now tomorrow I just get to review with you and then test this for you. If I was going to review one thing today, and there are some homework problems in here I would strongly recommend doing. But the one thing I'm most concerned about you forgetting is proving things are even or odd. Would you agree that f of x equals x squared plus 2x appears to maybe be even? If you forgot how this works, even things have y-axis symmetry, and odd things have origin symmetry, and that does not. I'm going to try again. There. So that's kind of an example of an even and an odd one from a picture, but what if you had to prove it? Do you remember the deal where you make them eat -x, f of -x? All right, so let's do that. F of -x, we're making it eat a -x. And then you simplify it. -x squared, the negative would disappear. but this negative would not. And then you ask yourself, was f of negative x equal to f of x? Was this actually f of x? No, it was not. So this is not even. We'll talk more about that again tomorrow, but I just wanted to get it back in your head because it's been a long time since we talked about those. Tomorrow we'll review everything. But if you don't practice this, the thing I just taught you, then it probably won't stick through to Friday. And this one thing, this homework assignment, this one thing could keep you from the A. You're probably, would you agree, and if you're human, you're going to make one dumb mistake on your hard problems on the test. Just naturally. You probably make one dumb mistake if you're not super careful. If you then also don't know how to do what we just practiced there, you can't get an A. If you make one dumb mistake and you don't know how to do this kind of problem, you can't get an A anymore. So, make sure you learn that. The homework is at the end, and you should do all of them, but I don't really expect you to do all of them. Just do most of them. That's all I have for you for the video for today.